Alright, so today we're going to talk about quantum numbers in organic chemistry. This is going to be one of the first topics that you will come across when taking an organic chemistry course. And it can be a little daunting at first, but I think if you break them down and try to understand what each individual quantum number means and how they relate to how atoms can engage in chemistry to form molecules, I think it'll serve you really well later in the course. So, as a general overview, the four quantum numbers you're going to see are n, l, m sub l, and m sub s. But before we go further detail into what quantum numbers are, let's talk about orbitals. So what are orbitals? Orbitals are basically a way to describe the wave-like behavior in an electron. And when I say wave, I'm not talking about ocean waves, I'm talking about sine and cosine. Additionally, they describe the highest probability of finding an electron. So, to illustrate that point a little further, if we look at a carbon-carbon bond, right, this is typically what you're going to see in a Lewis structure. It looks like the electrons are concentrated right here, but in reality, electrons kind of float around the molecule, and the best way to represent that is as a malleable electron cloud. Malleable electron cloud. They have a lot of energy, so they're moving around a lot. They're not confined or concentrated into a line between two atoms. They're kind of all around the atoms. And if you want to look further into representations of what that looks like, I encourage you to look up electrostatic potential maps, and I'm sure there's going to be an EPM diagram somewhere in your textbook, but if not, if you just do a quick Google search, I think that EPMs show they're really great representations of what that electron movement and concentration actually looks like, or how they're distributed in a bond. Okay, so now that we've covered that, let's go into quantum numbers. So we have our first quantum number, which is the principal quantum number. Principal quantum number. And that's described as n. N is the principal quantum number. And the range is going to be from 1 to 2 to 3, so on and so forth. Basically, any number greater than 0 can be a principal quantum number. And they primarily describe the distance between electrons and their relative energy in each orbital. So, to make that a little easier to understand, let me draw an atom. So we have the positively charged nucleus, that's a positive sign, and outside of that we're going to draw our energy levels. Let's just pick this color arbitrarily. So we have the first energy level and our second energy level. So the first one is going to be n equals 1, right? The second one is going to be n equals 2. Oh, I completely switched that. So this is going to be n equals 1, and this is going to be n equals 2. As you can see, the second energy level is farther away from the first energy level, right? So this distance, farther away from the nucleus. That distance to the nucleus is longer than this distance. Now, in each energy level, there are electrons in that energy level, and their amount of relative energy is going to be dependent on how far they are from the nucleus. So if you're closer to the positively charged nucleus, as you can imagine, your negatively charged electrons are going to be drawn towards it, and they're going to be less mobile and less able to engage in chemistry with other atoms to form molecules when they bump into them. On the other hand, the electrons in this energy level, n equals 2, are going to be more apt to interact with other atoms and engage in chemistry. So just to recap, because they're farther away from the center of positive energy in the nucleus, they're going to be more free and more mobile to engage in that chemistry. So that's how the principal quantum number can speak to the relative energy in each orbital. Moving on to L, the angular quantum number, angular quantum number. Its range is going to be from 0 to n minus 1. I'm going to replace that comma. 0 all the way to n minus 1. So, for example, if you had a principal quantum number of 1, then your L values would be 0. If you had a principal quantum number of 2, then your L values would be 0 and 1. So these basically describe the shape of your orbital. So remember, like I talked about earlier, orbitals describe where the electron's going to have the highest probability of being, because remember, they're not confined to a bond, they're moving all over the place. So these orbitals describe the relative area of where they're going to be. And for each L value, you have a different shape, right? So for S, you're going to have a value of 0. For P, you're going to have a value of 1. For D, you're going to have a value of 2. And for F, you're going to have a value of 3. S, P, D, and F are just letters that correspond to a specific shape. Mostly in organic 1, you're going to see S and P. So S, let me do this in a different color. S is shaped like a sphere, and P is shaped like a dumbbell. P is shaped like a dumbbell. Yeah, so L basically just describes the shape, and you're most commonly going to see S and P. But just for the sake of knowledge, D is going to look something like that. Moving on to M sub L, that's going to be your magnetic quantum number. Magnetic quantum number. This describes your orientation of the orbital. Orientation. So, for example, if you have a L value that corresponds to P, right, you can have values of negative L to L, or negative L to positive L. So, like I was saying, for the P orbital, you're going to have values of negative 1, 0, and 1. And they can correspond to different orientations. So you could have Px, Py, and Pz. Let me redraw those to make them a little neater. Px, Py, which basically the letter in the the smaller letter, I guess, refers to the axis that it's on, or the axis that the orbital is on, pz. Lastly, you have magnetic spin. Magnetic spin. And the only values you can have here, it's pretty simple. It's just positive and negative 1/2. So I'm going to go into more detail about this in a future video, but if you look at orbital energy diagrams, you see that orbitals are represented by lines, right? Little dashes, and electrons are represented by these arrows. So a upward facing arrow corresponds to a positive 1/2 value. Negative, or a downward facing arrow corresponds to a negative 1/2 value. So I'll go, like I said, I'll go into more detail in a further video, but this is largely responsible for why electrons in an orbital cannot have the same set of quantum numbers, right? Because even if they match all these numbers up to this point, they're not going to have the same magnetic spin because you can only have one of each spin in an orbital. So that covers the 4 quantum numbers you're going to encounter in Organic Chemistry 1. I hope that was informative. Again, please like and subscribe if that was informative and helpful for you, and I'll see you in the next video.